today's webinar on oil well cementing, organized by the SPE AMET student chapter in collaboration with Department of Petroleum Engineering AMET. My name is Nasrin. I am the membership chairperson of SPE AMET student chapter, and I will be hosting today's webinar. I am pleased to introduce today's speaker, Mr. Herman Camillo Pedrosa, who did his Bachelor of Science in Chemical Engineering from 2004 to 2010. After that, went on to do Master of Science in Nanotechnology Engineering from 2017 to 2019 and is currently doing his P.hd in Chemical Engineering in Norwegian University of Science and Technology, Norway. He was worked with Halliburton as research scientist cementing Brazil from the year 2016 to 2019 and has also been a lab engineer of cementing in Colombia, Argentina from the year 2010 to 2016. It's an honor and privilege for us, sir, to have you with us today. I also welcome the dignitaries, teachers, and my dear friends. I'm pretty much sure we will be enriched by today's webinar. Before starting today's session, we would love to tell our participants some rules and regulations they need to follow throughout. Please don't switch on your camera and your microphones. If you have any doubts, we would request you to put them in the chat box. We will be answering questions at the end of the sessions. We request our participants to maintain the decorum of webinar. So without any further discussion, I would like to welcome our presenter, Mr. Herman Pedrosa, to start the session.
Hi, good morning or good afternoon, everyone. First of all, thank you for inviting me here. And as they were saying at the beginning, I will give you an overview of oil well cementing operations or oil well cementing. So let's start with that. So, cementing, it's an operation of oil well drilling that is very important. Actually, it's extremely important, but sometimes it's, let's say, undervalued, or people are very aware of what that is. Usually, if I ask you right now, what comes to your mind when I say cementing, I'm pretty sure that the answer of many of you will be something like this. But actually that's not so far from the reality. At the beginning, oil well cementing was pretty much that. So it was just a bunch of people mixing cement together and placing it on the well. At the time, the wells were a little bit shallow, so it was possible to do that. But thanks to technology and more security or safety issues, we have been able to evolve a little bit. And now from this, we only rely on something like this for our well cementing operation. So that it's more like technological, automated, and it has more benefits for all. As a typical cementing operation, it looks something like that. This is only for land rigs. Offshore rigs are a little bit different, but in theory it's pretty much the same. So we'll have the rig, then we have the bulk cement or the cement silos, the water line or the water containers, and these two will be connected into the unit that I showed you in the previous slide. It will be mixed, and then it will be pumped down the drill. So that's pretty much the overall of how a cementing operation is done. But even though it sounds very easy and very simple, it has many things behind that. It has many things that people should care about before doing that. So in order to do this, the cementing technology and the cementing community has been evolving and has been creating some standards to be able to make sure that what we do is done in the right way. The first document or the first procedure that was launched on the market was in 1937, and from there it started to evolve with many techniques and many technologies. And as I was saying, it's something that it's evolving. And this year was launched the APA standards for stage cementing. That means that as new operational procedures are coming, as new technologies are coming, and as new challenges are also appearing, the industry needs to adapt to them. And in order to adapt in the right way, we need to create some standards. So that's the reason why it is still appearing some standards. In between these years, there have been much more standards, but I just thought these are like the most important to show you. So now I want to tell you or to ask you to put on your mind, why do you think it's important to cement an oil well? So there are many answers that I might heard if I were over there with you, but the main reason or the objective is to get a good zonal isolation. That's the main point of cementing. So you can avoid any communication between zones. If you have a reservoir, it won't communicate with water reservoirs, or it won't communicate with the surface. Or if you have a water reservoir, it won't go through the surface. So the main objective of cementing is zonal isolation. Of course, there are other secondary objectives that are very important also. That's just, it can be like hydraulic seal or work as a casing support or protect the casing or abandon the well. So there are many other like small objectives, but remember, the main thing is zonal isolation. And the reason for that is because we don't want something like this to happen. This is an active volcano on Yellowstone Park
Hello,
in
sir.
the US.
So we are
But
getting that many of
if
them are not,
we
the
have
request is not been
problems
accepted,
with
sir.
zonal isolation,
We are
we
getting calls.
might get something like that.
They are calling us and
That's
telling
what
they
we
are
want
not
to avoid.
accepting and like that, sir.
So that's the huge importance of zonal isolation. This is why it's so important, and the companies invest
Okay.
millions of dollars on doing this,
Okay,
because
sir. Okay, sir.
this will save us and save the environment for
Okay, sir.
many catastrophes. So
Okay, sir.
there
Okay,
are
sir.
two types of cementing.
Okay, sir.
One of them is the primary
Yes, sir.
cementing, that is like the most common type, and it has some important factors or displacement factors in order to be able to improve the quality of the cement. So we need, for example, oh, yeah, we need the mud conditioning. We need to use some tools or scratchers to clean the well before or while cementing. Use some spacers and flushers to be able to also clean the well, to take out the mud. Also, it is recommended to do some pipe movement if possible. So there are like reciprocation and rotation. Some wells, it's not possible to do that, but when it's possible, it's recommended to do it. And the other factor that is very important is the flow velocity. It's always recommended to go as fast as you can, like to pump the cement as fast as possible. Of course, without getting into the fracture area. So just to show you like a schematic of how it's cementing done, we have here a well that it's just full of mud, and we have been conditioning the mud. So what do I mean by conditioning the mud? It's that in order to clean the well of the mud, we lower some properties of the mud, like the viscosity and the yield point. And why do we need to do that? It's because as we're isolating some areas, we need to remove the mud completely. If we don't do that, after it sets, what happens is that the mud will dry and will leave some channels. And if we have channels after cementing, actually we'll have problems because we won't have any zonal isolation. On those channels, anything can flow and the different areas can get some communication. So the first part is conditioning the mud. Then we will start pumping the spacers and flusher. That it's the blue part that you can see there. Then we put some plugs. This orange one, it's called the bottom plug. It's very important for a primary cementing operation to have these two plugs. Actually, pretty much all of the cementing operations are done in this way. So we start pumping the lead cement, and it will go down, and after that we will pump the tail cement. So just to explain a little bit what's the lead cement and what's the tail cement. The lead cement, it's a cement slurry with lower density and somehow with lower quality. That cement, it's pumped first because at the end it will be on the upper side. So usually what we do is that we put the tail cement, that's the most important. That's the cement that has all of the properties that we need. But in order to fill up the wellbore higher with cement, and in an economical way, we use a lead cement or a secondary cement that will give us some hydraulic seal, but at the same time it won't be so expensive. So that's the reason of the lead cement. So when that happens, after that, what happens is that a plug will reach the landing collar, that is this part, and it will break. So once the bottom plug breaks, the cement can start flowing through the annulus. So it will start flowing through the annulus until this second plug, or called the top plug, reaches the first one. This plug, it won't be possible to break. So you can apply pressure here and it won't break. And in order to do that, we will use a displacement fluid. It can be water, it can be drilling fluid, it depends. And for us to know if the cementing operation was done properly, we applied some pressure here to see if we can build something like some pressure. If we cannot build pressure, that means that we still are having some communication. So that's somehow like a quick overview of how a cementing operation is done and how and what happens down the well. So as I mentioned before, here in the upper part, you will see like a lighter cement, that's the lead cement, and underneath it will be the tail cement or the main cement. So the piston and everything will be located on that part. The upper part, it's just to help a little bit with the hydraulic seal, but it's not the most important area. Here it's an schematic of the well. Of course, we don't have like only one cementing job. It's different cementing jobs, and it will be one for each zone. So we will have the reservoir, and it will be a cementing operation here. We have another area of interest, and that will be like another cementing operation here on the intermediate casing, and on the surface casing we will have also some cementing operation here. As I mentioned, cement it's expensive, so usually it's not, the wells are not cemented all the way up. So the engineers, the reservoir engineers and the cementing engineers, what they do is they calculate what should be the top of cement, and they cement until that point. It's useless to go after like above that. It's just like wasting money. Of course, some wells require that, and in those cases it has to be done. But in some others, it's not necessary to go all the way up to fill the well with cement. And the second, so I was talking here about the primary cementing. That's the cementing that it will be between casing and annulus after you land the casing. And then we have the secondary cementing, or also called remedial cementing. So why is this used for? Usually like for shoot off unwanted water of gas or gas, repair primary cementing jobs, abandonment of non-productive or abandonment of wells, seal of trouble zones that were or that appeared during drilling, and also to isolate formation prior to perforating. That's in cases that we have like a complicated formation that we need to give more stability, or to to isolate from the drilling fluids. This can be done. Also to repair mud or gas channeling on primary cement jobs, as I mentioned before. If there is leftover of mold during the primary cementing, we will have some channelings, and if we have those channels, we will have communication. So then we will have to do remedial cementing. Then also insufficient top of cementing primary job, and repair casing leaks. That was the repair cementing, but also on the secondary cementing operations, we can find the cement plugs. They are also used on or for different reasons. It depends on the reason of the plug, the name. So we have one of the most important, and that nowadays it has been very used, because we're getting old wells that need to be abandoned. So the well abandonment is just to put cement plugs pretty much in every area or every zone that was of interest or had a previous casing before. So it will seal the well completely. As you can see here, we will have to put some cement plugs all over the wellbore to seal every single section, as I mentioned before. Also, we have another type of cement plugs that is called, or to do side tracks, or to change the trajectory of the drill bit. Sometimes this can happen of something that it's programmed on the drilling program, that you want to have like a dog leg, or you want to have a deviation. So what we do is to put a cement slurry that it's extremely hard. So when the drill reaches that point, it will be forced to bend a little bit to the side, and then it will change the trajectory. Also, side tracks are used because of problems on the well. So on this image, you can see like this can be a tool. So during drilling, you can have problems where you lose a tool. So what it's done is that a side track or cement plug is put above that, so you can deviate the trajectory and start going to another, like it is, and can start or continue drilling on the same, pretty much on the same direction, but from another path. This cementing is also for zonal isolation. So plugs for zonal isolation. That means that maybe you reach an area that you didn't want to reach. So what it's done is we put a cement block a little bit above that area, so we can have like a new bottom somehow. That way we can leave on the store the area that we didn't want to disturb. So in this case, we have a pay zone and the wet zone. So we don't want any communication between the wet zone and the pay zone. So we put a cement block to separate these zones. Also, when you have lost circulation zones. So a lost circulation zone, it's an area, or it's a part on the well that it's taken away. It might be fractured, or it might be like naturally problematic. And the importance of this is that it will lose a lot of drilling mud. So it is very important to control that area. So what it's done is to put a cement block there to avoid the drilling well to be lost. So I have talked to you about pretty much the cementing operation, how it's done, how it's performed on the well, the types of cementing operations, but there is something that is very important on this, and it's what we use, and that's the cement. I remember when I started working on this, some people used to say that cementing was something that was like really easy. Just mix cement and water as if you were like just building a house or putting some concrete down the floor, and just send it to the well. And actually that's not true. It has a lot of science, and it has a lot of important things to consider. So now I'm gonna talk to you a little bit about what is cement. So cement, it compromises mainly four things, or four components. That's the sodium tricalcium silicate and the calcium silicates. Those two are the ones that are going to give the strength to the cement. Those two are the ones that will give the mechanical properties of the cement. So they are the main components of our cement. But also we have tricalcium aluminate, that it's a very important part. It will help us with the initial reaction, and we have the tetracalcium ferroaluminate that will help us to control the aluminate on the tricalcium aluminates. So I go a little bit fast through the boring part, that it's or for some, the boring part, that it's the chemistry of cement. So mainly what we have is, as I mentioned, the tricalcium silicate and the decalcium silicate. They mix with water, and then they start to create the CSH, that it's calcium silicate hydrates, and some calcium hydroxide. So what will give our cement the strength? It will be the calcium silicate hydrates. That part, that component, it's the one that will give you the strength on the cement. So the more CSH that you have, the stronger that you have the cement. So that's the main part. So as I was mentioned before, on the these are like a chart of compressive strength. So the calcium aluminate and the calcium ferroaluminate, they won't help you, or they won't give you so much strength on the cement, but what will give you the strength is this calcium silicate, the calcium silicate and tricalcium silicate. One of them will react faster and will give you the initial strength, and the other one will take longer, but will give you, will develop some strength after time. As this, as the calcium silicate, it's something that takes time to react. Actually, something that happens that the cement, if it has water, like contact with water, it can continue reacting. It can continue building some strength even after many years. So that's something that's kind of interesting. And now I will talk to you a little bit about how it occurs the cement set, because I guess that as many of you know, cement is a liquid. We mix water and the dry powder of cement, and then it starts to react and it becomes a solid, let's say a solid rock. But what happened is that here on the stage one, we have the moment where the cement starts to react with water. It will release some heat. Then we have the stage two, that it's called the dormant or the induction, the dormant part or the induction. It takes a couple of hours. Well, I'm not gonna give you like the full chemistry of that, but what happens pretty much is that the ions will start to, let's say, reaccommodate. And after that happens, we have the acceleration part. And you see a bump here, that's because it's an exothermic reaction. So when the cement starts to become CSH, it will release heat. And then we have this acceleration part. That means that it's already reacted. We have already like a set cement or a hard paste. And then we will start having the solid cement that we know. And that will take like a couple of days. Usually in a cementing operation, there are a few things that are very important. So one is the time that cement will be fluid. So this will be the dormant part, because that time it's the time that a cement engineer will have to conduct the cement operation. And then the other important time will be the steady state. So when it has reached certain type of strength. Because what happens after we place the cement is that the well should be shut down so they can give time for the cement to set. Usually it can take between a couple of well, not a couple of hours, but between some hours, let's say 6 hours, to even a couple of days. It depends on many factors. But the operations on the well should stop after the cementing place has occurred, because if they perform any other activity, what could happen is that the cement sets in an unwanted way, so it can create some channelings, or it can set improperly. So this is the reason why these stage 2 and stage 5 times are very important to know. This is a little bit of what happens on the cement grain. So it's a plain cement grain, and it will start reacting with the ions. It will start getting something called ethringite, and then after that ethringite is created, then we'll have some the CSH, that it's this last part. But I guess that's not many important for some of you that are not going to work on this part. Also, the cement as it is, it's something that it won't fit to every single well. Some wells can be cemented just with water and cement, and that's it. That'll be perfect. But also, some wells need some additives in order to reach some properties, or in order to acquire some properties that are needed to fulfill or to overcome a challenge. The main additives that exist are these ones. So, and also they are named after the challenge or after the necessity that they are, or they overcome. So we have the accelerators. That means that sometimes we have a cementing operation that won't take so long. For example, it can take just half hour of operation. So if we have a cement that will set, or it will become solid after many hours, after 10 hours, that will be a problem, because we will be wasting time just waiting for that to happen. And as I'm pretty sure you all know, an hour on the rig, it's very expensive. And now it's even more dangerous to just waste money waiting for something to happen. So this is the reason why we use accelerators. So if we have a cement that sets in 10 hours, we can put some accelerators and we can have it set in 2 hours or in 1 hour. So it depends on our placement time. And also we have the retarders that are pretty much the opposite. So if we have a cementing operation that will take 10 hours, and we have a cement that, because of the heat, because of the properties, it will just set in 4 hours, we will need to put some retarders to make the cement fluid during a longer time. Also, we have dispersants that are used to lower the viscosity of the cements. We have viscosifiers that are the opposite, to increase the viscosity of cement. Those are many important things that should take care of for a good cementing operations. The importance on the viscosity will be due to the ECD. Then we have the fluid loss control, gas influx control, densifiers, lightweight additives that are, the densifiers are to give more density to the cement, to make it higher, heavier, and the lightweight are the opposite, to make it lighter. We have many types of additives to do that, and on the lightweights there are also different techniques to do it. You can, some companies do foam cement, that it's putting some foam, some air to the cement, so it will create some bubbles, so it will have a lower density, but with some really good mechanical properties. Or sometimes they only, what they do is to use other type of materials that will lower the density but will continue increasing the mechanical properties. Then we have retrogression control additives, that those are very important when you're cementing a well that it's above 100 Celsius degrees Celsius well, or 230 Fahrenheit degrees, because after that temperature, what happens is that the chemistry in the cement will be affected, so it will start to break the CSH. So we need some additives to overcome that problem. We also have expansive additives, loss circulation additives, and there are now some new technologies that are coming to the market that are the resins or composites. So instead of using cement, they are using resins because you can get much better mechanical properties, or the combination of these resins and cement. These are pretty much the most important additives that they are, but there are other types. Also, there are other type of cements that, according to the operations. So, for example, when cementing a geothermal well, a specific type of cement should be used. Also, there are some companies that have some cements that are that have other kind of chemical structure, so it will give some other properties, but that's just giving or looking into more specific challenges that are not into this case today. And in order to know if the additives that we're using are right, the cement that that we're going to place, it's the proper one according to our channel, according to our challenges, according to our conditions, according to the well. It's very important to test the cement, to do all of the tests, so you can not be sure, but at least so you can control many parameters on your cementing operations. So the things that we control usually are the density of the cement. Why is it important? It's very important because on the calculation that it has been done, usually you have like a small window, like operational window on pressure or ECD. So if your density is heavier than your operational window, what happens is that you may fracture the formation. But then if your density is very low, what can happen is that you can have gas influx because you don't have like enough hydrostatic pressure to control it. So that's very important. And we do it just like with a regular mud balance that I guess many of you know. Also, what we control is free fluid. The free fluid, it's just like the water that it's just like if the cement has sedimented and we have some water on top. If we are cementing a vertical well, that can be an issue, but the problem is that the top of cement won't be as high as we want to. And it maybe won't be so problematic. But if we are cementing a deviated or a horizontal well, that will be a huge problem. if we have some water on top on a horizontal well, that means that we have a channel of communication. So that is a huge problem. And the way to check it is with these probettes, where you just put an inclination on the cement while it's setting, and you check the amount of water that it's on top. Usually, the accepted water is 0%. So it should not be any water on top of the cement. Then we have the rheology. So the rheology will help us to know what's the viscosity of cement. As I mentioned before, the ECD is something that is really important for us. If we have a high ECD, we can damage the formation. And a way to increase that ECD is with higher viscosities. So if we have a really high viscosity on the cement, we may have that kind of problem. But then some people will say like, okay, just then put a lower viscosity. And the problem of a lower viscosity is that if we have a mud that is viscous, we won't be able to displace it. An example of this is, for example, if you have honey that is a viscous liquid and you're trying to displace it with water, well, what will happen is that the honey will stay and the water will just go around. So what we need is to do the opposite, to have some fluid and to have a cement that it has a higher viscosity. So it's like if you have water and then you're displacing that water with honey. So the honey will displace completely the water. And the way to do this, or the way to measure this, is by using the viscometer model 35. This is, you will have them in every single lab, cementing lab, and also many of the mod labs. So it's a very easy technique to check. Also, the fluid loss control. The importance of this is that the cement doesn't lose the water, because if, as I showed in the beginning on the reaction part, what will give the strength to the cement is the reaction of the cement, or like on the dry cement or the cement powder with the water. So if we lose the cement, we won't get the strength that we need to. Also, we won't get the height of the cement that we want to. So I guess that a way to explain the fluid loss control is if, for example, you go to a river or to the sea and get some sand on your hands, you will see that the water comes out of your hand, and you will have like a paste of sand or of earth that you can like move it, and it's very breakable, so it doesn't have any mechanical properties. That will happen also to the cement, so that's very important to control. And the apparatus that we use to check on these properties, it's the fluid control press. So we will just apply some pressure on the cement and see how much water it will release. Also, we have the thickening time. That's for some people, it's called like the queen of the testing. So it's one of the most important things, because it will give you the time that you have to do your operation, your cementing. What we use, it's a consistometer. So on this equipment, we will simulate the pressure, the temperature, and the movement that the cement will have. And we will check the time. So what we see is like how much time it will take for the cement to change from being a fluid to becoming a solid that it's not pumpable anymore. So it's very important to know that in order to be able to finish your cement job in a proper way. Then we have the comparative strength, that it's the property that will give you the, as it says, the strength of the cement set. There are two ways to measure it. One way it's the destructive way, that it's just to put a cement set and break it with a press. Then you will know what's the maximum load that it can resist. But the problem of that one is that it's only in one point of time. So for example, if you set a cement during 8 hours and you break it, you know what's the strength of the cement at 8 hours. But that strength will be different at 12, at 13, or 24 hours. So now what the industry uses, it's the ultrasonic cement analyzers. That it's a way that just by looking at the wave velocities, it will check how it's the cement reacting, or how it's the cement changing from liquid to solid, and from solid to getting harder and harder. So it's very important in order to know at what time they are on the rig able to start conducting other type of operations. So for example, after the cement has reached 100 psi of strength, they can start doing some small operations. But when cement has reached 500 psi, they can do more operations that are like releasing casings or other things that are like more important. And in order to continue drilling, they will need to reach 1000 psi. And for example, if they are gonna do some canyoning, they will need at least 2000 psi. So those times are really important in the rig in order to know at what time they can continue working, so that they won't have to wait long time on the rig just for the cement to set or just to give some time. So for them it's very important these times so they don't waste time. Also, another important parameter is the static gel strength. It will help a lot because the cement, when it's changing from liquid to solid, there are a few minutes that it will be like a gel, like a type of gel. So it won't control the gas influx by hydrostatic pressure, because it's no longer a liquid and it won't have hydrostatic pressure. And also it won't control the gas influx as being a solid, because it's not yet a solid. So it's very important to know what is this time, so you can control, or you can see if you can have any gas influx or not. And we do that using a static gel apparatus. There are several types, and this is one of them. Also, we check the mechanical properties. One of them is the elastic modulus, that will tell you like what's the elasticity of the cement. I know that it sounds weird because cement, it's just like a rock, so it's hard, it's not elastic. When you hear about something elastic, you can imagine rubber. But any type of material, it has some type of elasticity, and also the cement. So this elasticity will be important because if you're having loads or cycles on the well, the cement will be or reaccommodate itself somehow, and in order not to break, but just to overcome those cycles. So also it's very important to know the elastic modulus of the cement. Then we have the permeability. We'll tell you what's the importance, or if you can have any communication, and for that it's use a permeameter. And yeah, that's pretty much all of the information that I wanted to share with you. I hope you have liked it, and I hope you got to understand a little bit of what cementing is and what's the importance of cementing and what are the challenges and the science behind cementing. So if you have any questions, please let me know.
It was a wonderful session, sir. Now moving on to Q&A session. So the first question is, what will be the exact density for the good cement job?
The exact density, it will depend on your formation. There are two types of cement that are used on cementing operations. There are class G and class H. So those will give you, or those cements have a natural density. So class G, it's 15.8 pounds per gallon. So mainly when there is no complication on the wells, that will be the density that will be used. Or if they are using class H cement, will be 16.4 pounds per gallon. But also, if you have a depleted well, or if you have you're on an area that it has a fracture gradient that won't let you use those densities, you'll have to lower the density. It can be with some additives or by forming the cement. So it will depend on your well, but those are like the most typical densities that are used.
Okay, so the next question is, how shoe test and leak-off test will be responsible for the good cement job?
I'm not sure if I understood that question. So how a leak-off test influence the cement?
No, how shoe test and leak-off test will be responsible for good cement job?
Okay. So if I let's see if I can answer that, or if I understood the question. So the leak-off test, it's done to check the formation. Let's say like the strength of the formation. Usually it is done after the cementing job has been done. It's drilled a little bit, like the cement, it's drilled down, and then you get to a new formation or a new, let's say, section. Usually the cement, it has higher mechanical properties than the formation on that part. So when you do a leak-off test, the compressive strength of the formation, it's lower than the compressive strength on the cement. So it will, or you will have, or you will see the change on pressure when you do the leak-off test. When or when you see the change on the pressure on the leak-off test, you are checking on the formation damage, not on the cement damage, because the cement has a higher compressive strength, so it won't break as easy as the formation. I guess I'm not sure if that's the answer or that answer as it's for the question. I'm not sure if I got the question right.
Okay, sir. So the next question is, how should we contrast between guide shoe and flat shoe, float shoe?
Between guide shoe and float shoe. Okay, so they are pretty much the same. The guide shoe, it's when you're running the casing down, you will have or you will need a shoe that will help the casing to go down and not to get stuck on the formation. And pretty much that same shoe, it will have the property of being a float shoe. Actually, what it's used is the guide shoe and the float collar. They are always used together, and the float collar it's the part where where both floats would land. So that's like a common arrangement when you're lowering the casing to have the guide shoe and the float collar.
Okay, so the next question is, if we put cement in casing with some pressure, how we generate that pressure?
If you put cement with pressure, so when we're pumping the cement down, we use pump on the surface, like some pumps on the surface. So that's the way to increase the pressure. But nowadays they are doing some other type of cementing jobs that are like managed pressure cementing. So they close the annular, and from the choke they will also control the pressure by opening and closing valves and the drilling fluid. So if you're pressuring from the drilling from the annulus, it will be the drilling fluid that will give you the pressure. They will use the choke on the surface to control that pressure, like opening or closing the valves. If it's closed, you'll have a higher pressure. But if it's inside the casing, you will control the pressure by the pumps on the cementing unit.
Okay, so how can we calculate the number of barrels in cement operation?
The barrels on the cement operation, it will depend on the top of the desired top of cement that you want. So you know what's the height that you wanted to reach, and also the diameter of the well that you have, and the diameter of the cement of the casing that you have. So the engineers will calculate this using those two diameters to know like what's the void space that they have to fill, and also with the height. So those are like the three dimensions that are necessary in order to calculate the volume of the cement. And once you know the volume of the cement, you can calculate the barrels.
Okay, so the next question is, if we are dealing with high pressure, high temperature wells, so what kind of additives will be suitable for that well?
All right, for that, one of them is that the cement will be in a temperature above 230 degrees Fahrenheit. So it will need some retrogression additives that it's mainly sand. So you will have to use those. But the other additives, it will depend on the like other properties like the like fracture gradient and all of this. So mainly for high temperature wells, it's to use a retrogression agent. Um, and yeah, that's pretty much the only concern that are needed.
Okay. If the gas influx occurs, how to solve it?
The gas influx is a huge problem on the industry, and depending on the well, it's not a straightforward answer. So the main ways to control gas influx is by having an hydrostatic pressure that is higher than the pressure of the gas or the gas that it's coming. So that's one of the reasons, but also if you have a fracture grading that is low or a fracture grading that is close to that, it can be a problem. And the other way to solve it is that from the cementing perspective, we use additives that will give the cement the ability to control that. So there are like we will check what's the criticality of the influx. So if it's a lower influx, we can just control the height of the cement. So the height of the cement will give the hydrostatic pressure, and that will be it. So good fluid loss control, it will be perfect. If that doesn't help, or if it's like let's say a medium gas influx, there are some specific additives that will lower the time or the gel time of the cement, so that it will, as I mentioned before, the cement will change from liquid to solid, and that's the time that it's not liquid nor solid. If it's according to the API specification, if it's higher than 45 minutes, it will be a problem for medium or criticality of medium gas influx. So what we try to do is just use additives that will lower that time, that will make the cement go from liquid and go through the gel phase faster. And if we have a really high gas influx, what it's done is that we can use foam cement, because, well, actually a foam cement, it's a cement with gas, so that won't be like, that will, like, if we have more gas coming, that won't be such a problem. Or also expansive cement. So what we can do on that, it's just that as we have like some attack of gas, the cement will let's say attack back by expanding itself. So it depends on the criticality, what kind of additive it should be used.
Okay. Can you please explain the retrogression additives?
Yeah, so what happens on temperature is that after the cement reaches that 230 degrees, it will the CSH will react and will form some calcium hydroxide. So yeah, the explanation will be a little bit like chemistry. So it will create some calcium hydroxide, and the problem is that calcium hydroxide, if it's enter with water, it can like dilute and go away. So the cement will lose volume. So when we have sand, what sand is silicon I forgot the word in English. Iodide, silicon iodide. So that silicon dioxide will react back with the calcium hydroxide that has been formed again. So when they react together, they will create again some CSH. So these additives are just mainly sand or material that will have a silicon oxide, and this silicon oxide will react with the calcium hydroxide that it's released due to the high temperature. So when they react together, it's just like a cycle. So the cement will create calcium hydroxide, then it will react with this silicon dioxide, it will create that CSH, and then that CSH will come back and create calcium hydroxide. So it's just like a cyclic reaction of that reaction, silicon oxide and calcium hydroxide. So that's how that's how these additives work.
Okay, so the next question is how the cementing is done in shale gas formation in horizontal well without the cement sheet getting fractured.
Uh, can you repeat that again, please?
How the cementing is done in shale gas formation in horizontal well without the cement sheet getting fractured.
Okay, for that, it's important to know what will be the cycles or what will be the operations after the cement has been placed, and in order and once you know that, you will start testing your cement and testing the mechanical properties. One thing that I said on the properties was the elastic modulus of the cement. So what it's done is that you check that elastic values to see if the cement can react. So imagine that you have a rubber, so you can press it, you can release the pressure, then you can press it again, you can do many things, and that rubber won't break. That rubber just will reaccommodate itself. So pretty much that happens with the cement. So when we have the several operations that can be more critical or that will demand more of the cement, we will check what's the required elastic value, and we will add some additives to reach that. So sometimes polymers are used to enhance the elastic value, like the Poisson ratio of the cement. So once you have reached an elastic value that it's good enough, you know that that's the formulation that you can use for a cement that will have several cycles or several pressure up down operations. So that's what we used, or that's how we know how to, or how the cement will withstand the operations afterwards. And usually for this, some softwares will be used, like to know or to simulate according to the parameters of the cement and according to the operations that will be done. And then those softwares will give you or will tell you if the properties that you have on the cement will withstand that, or you need a higher elastic modulus.
Okay, so what is the cost of primary cementing in normal wells and high pressure, high temperature wells?
What is the normal cost?
What is the cost of primary cementing in normal wells and high pressure, high temperature wells?
That is something that I won't be able to answer, to be honest. It will depend on many things. As one one of the things will be the company that will provide the service, and the type of location, or many things that are not, let's say, into my area of knowledge. So that I'm sorry, but I won't be able to answer you this, as it's not something that I know.
Okay, sir. So, what is the maximum density we can increase when gas influx occurred?
It depends on your well. So the fracture gradient of your well will tell you that. Um, they have, I have heard of heard well, or work with wells that we had densities, like cement densities of 24 pounds per gallon cement. That it's like extremely high, but that's because the well accepts that, like the fracture gradient was good enough for that. But there are some times that your fracture gradient won't allow you to increase the density. So it depends on your operational window gap that you have.
Okay. So, someone is asking to explain how multi stage cementing is done and how we determine whether we need to go for it or not.
How cementing? What?
How multi stage cementing is done and how to determine whether we need to go for it or not.
Okay, stage cementing. Um, um, uh, Usually, one of the reasons that I'm aware of that it's used is when you have a long column of cement to be done. So let's say, for example, you want to cement a huge part of the well. Uh, what happens is that if you put too much additives in order to have enough time to cement that, you will have to wait longer for the cement to become solid. So to avoid that, what it's done is that you cement first one part and then the other part. So, and then that's like in two stages. That's how it's done pretty much, and that's one of the reasons that I'm aware of. The other one, I think it's because you have a formation that it can break easily. It can fracture very easily. So as the cement, it's something that it has a density higher than the mud. If you put some cement, uh, your hydrostatic pressure will be higher than your fracture gradient, and then you can break the formation. So what it's done in these cases also is a stage cementing, so you can cement one part, wait until it sets, and then cement the other part. So then you won't have so much problems with the fracture gradient. And well, the tools for that, there are different tools, but yeah, like I'm not very sure on how, like, the mechanical functionalities of those tools. So yeah, maybe by explaining those tools, I be confused, or I might confuse you. But that's pretty much that's how or the reasons why I know that it's stage cementing is done.
Okay, sir. So, will it be possible to share the PPT with the participants?
Yes, I can share the PPT with Pulmani and Onkar, and I guess that they will have the list of the participants, and they can like share it back with them or with you.
Okay. So, due to time limit, we will be replying all your questions through mail. Thanks for the brief explanation, sir. I hope the participant got their answers for their questions. It was
All right.
indeed, yes, sir.
No, thank you for inviting me, and It was a pleasure for me.
Yes, sir. It was indeed a privilege to have Mr. Herman Camillo Pedrosa, who gave us an insightful lecture on oil well cementing, which was full of wisdom and loads of information. Thank you for the knowledgeable session, sir. I hope all the participants might have got an idea what is actually oil well cementing and its applications in the industry. We appreciate your efforts, sir. On behalf of SPE AMET Student Chapter, we thank you for joining us. An event of this dimension cannot happen overnight. The wheel starts rolling months in advance. We have been fortunate enough to be backed by a team very motivated and dedicated. So, special thanks to Honorable Vice Chancellor, Registrar, and we thank to our management, Dr. T. Nagalakshmi, Head of Department of Petroleum Engineering, Faculty Advisor, Mrs. Ponmani Swaminathan, and the office bearers for letting us to carry this event successfully. And last but not least, thanks to students for their patience and participation. In case if anyone has missed this session due to some problem, we will be uploading the session on our YouTube channel, SPE AMET Student Chapter. Thank you.